Hey everybody, we're continuing to talk about different forms of measuring variability here. Previously, we've learned about basic measures like the range and deviation scores, and our more complex measure we call the variance, and the two different ways of calculating that, both of which you should be familiar with. Now we go one step farther and talk about a somewhat more common measure of variability, the standard deviation. So here's the deal. We've learned how to calculate the variance, and the variance is a core part of a lot of statistical calculations. The thing is, the variance usually isn't reported, and here's the reason why. When you square scores, obviously they get a lot bigger, and the bigger the original score is, the more massive the increase has when you square it. What this means is essentially that scores that are really, really unusually far away from average wind up getting huge squared deviations, and they distort the variance. They make it seem bigger than it actually is. Because of that, the variance is usually converted to a more commonly used descriptive statistic, what's called the standard deviation. So, standard deviation is fortunately super easy to calculate. Here's our variance formula right here. This is the variance itself. Notice the variance is s squared. We turn it into the standard deviation represented by s by just taking the square root. So literally, you calculate the variance, you do one more step, and you have the standard deviation. The standard deviation is roughly the average deviation score from the mean. I don't know why that last line showed up early, but gosh, it sure did. So you can think of the standard deviation as basically undoing the squaring that happened when we calculated the variance. So we squared all those deviation scores, it made the variance too big, and we take the square root of it, and we sort of revert it back to something that's a little bit more normal, a little less distorted. So the standard deviation can be thought of as the average deviation score. It's also the name of like every crappy band and intramural team of stats grad students that I've ever known. It's like, get it, where the standard deviations. It's a little stats humor. It's a little goes a long way. So anyway, that's the standard deviation. We calculate the variance, we take the square root, and the reason why we do that is to undo the distorting effect that squaring those deviations has. So to recap all of that, we have again our point of emphasis. So as we've said a couple of times, deviations work just fine for individuals. They're terrible measures of variability because the scores always add up to 0. The variance gets around this by squaring those deviations, which makes them positive or perhaps 0, and then averaging them together. But now, if you have unusually big deviations, it leads to the variance being much larger than it ought to be. We undo that again by taking the square root of the variance itself. So that's one of our points of emphasis. That logic is going to be relevant to some of the later stuff we'll talk about. But for now, let's look at calculating the standard deviation with a new data set. Here what we're measuring is people's self-esteem scores. We're going to calculate the variance and the standard deviation using the definitional and computational formula. Notice our variance formula is down here. The standard deviation formula is down there as well. So here's our first column for all the individual scores. We add those up and we get 43.1. We calculate the mean by dividing that by the number of scores, which is 10. So the average self-esteem score is 4.31. Pretty straightforward. X minus m, we simply subtract across. And again, 5 minus 4.31 is 0.69. 3.9 minus 4.31 is negative 0.41, etc., etc. Notice if you added all those up again, they would add to 0. Instead, we square them. We round to 2 decimal places, as we generally do in this class. Don't go writing down all 7 or 8 decimal places that your calculator gives you. Not useful. We go to 2 decimal places, the first 2 non-zero decimal places. So these are our square deviations. When we add them up, we get the sum of squares, and that's 1.35. The step to turn it into the variance is just to divide it by n, and that just moves the decimal place over 1. So our variance is 0.135. We turn that into the standard deviation by just taking the square root. Square root of 0.135 is 0.37. That's our standard deviation. Let's look at the same data set with our computational formula. Again, sigma x is going to stay the same. Our animations are a little out of order here, but we have sigma x, which is the same as the definitional formula. All that we have to do next is square each score individually and add all those up, and that's all that we need. By the way, if this is starting to get complicated, again, this is a good example to go sit down with and try to start from the beginning and see if you can get the same numbers I'm presenting you here. Good to practice these equations. In an in-person class, we'll be doing quite a bit of that, but online that involves me just staring at you blankly for 15 minutes at a time. I think you get enough of that with these videos. So we add up all those sigma x's, we add up all those x squareds, the squared individual scores, we sum them up, we get 187.11. Only other info we need, we have 10 scores, that's our n. So we're going to do this on a different slide because otherwise it gets real crowded. But here is our sigma x, all of our scores added up. We're going to square that. Here is our sigma x squared, that second column where all the scores were squared and then added up. After squaring 43.1 and dividing by 10, we get 185.67. We subtract, we divide by 10, our variance is 0.134. Now here's an important note. Sometimes if you round at different stages of the process, you might wind up with a score like we have here that's just a tiny bit different than, say, the other formula or than what the listed answer is. This is generally called rounding error. Rounding error is totally fine. We don't mark off for it. So if you're off by 100th or here 1,000th of a point, you probably just rounded at a different point in the process. If you're off by more than that, 1/10 of a point or a full point, you probably made some mathematical error. So only for those tiny, tiny little differences do we call that rounding error. Anyway, here we get a variance that's very slightly different than the one that we got using the definitional formula, but it still winds up turning into the same standard deviation, 0.37. So that's the end. That's how to calculate standard deviations. Again, I recommend getting a little practice there on your, from your book, from our practice problems, and from your homework. Those are important calculations, but also understand the logic behind them as well. There's going to be quite a bit on that too. Next up, we are going to wrap up this module by connecting our variability concepts to our different populations, those different distribution shapes. I will see you there.